Welcome to Software Engineering Daily. Hadoop has been around for a decade, and many engineers who use it today were not writing software when Hadoop was first created. To understand the present of the Hadoop stack, you have to understand the project's past. Today's episode is a reading of a Medium post called The History of Hadoop. I was preparing for an upcoming interview with Mike Caffarella, the co-creator of Hadoop, when I read this Medium post by Marco Bonaci. And in this post, Marco talks about the entire history of Hadoop up until the present, from the inception of Hadoop to when Doug Cutting was working on the Nutch web crawler to the present where we have Spark and the entire Hadoop stack and Yarn and all these other supporting technologies. So Marco Bonaci gave me permission to read this Medium post for an episode, so I'm extremely grateful to Marco. He's also the author of a book called Spark in Action. I urge you to check it out or follow him on Twitter. So this is different from the normal interview format, and we'd love to get feedback on whether you enjoyed it. Software Engineering Daily is made for the listeners, so if you don't like this episode, if you want something different, if you have anything else in mind that we could do that you think would be interesting, please send us an email or contact us on Twitter, send us a tweet, contact us in the Slack channel. So yeah, with that, let's get to this episode. You don't have to settle for a job that makes you unhappy, and you don't have to go through the pain of searching through millions of job listings. Hired.com brings job offers to you, the engineer. Hired is a job marketplace built for the engineers. A few years ago, I was unhappy with my engineering job. I felt stuck, I felt underpaid, I felt alone, and I didn't know my value in the job marketplace. It's a very opaque market. So I used Hired.com to find a new position. Hired connected me with a talent advocate who guided me through the process, like a free concierge. They made me feel valued. It was like a white glove service. And this talent advocate helped me with all the questions I had. Should I ask for more money? Should I consider relocating to try to get a higher salary or a better job? The talent advocate that you get paired with on Hired.com helps you with all these kinds of questions. I got several job offers, and I found one that was a good fit. In fact, engineers who use Hired.com get an average of 5 offers from great companies like Facebook, Uber, and Stripe, and the companies are bidding on you to try to get the best engineers, and so you end up with the higher salary. Go to hired.com/sedaily for a $4,000 bonus upon signing up. It is completely free to engineers looking for a job. I've interviewed the founder of Hired, Matt Mitchkovich. He also started 99 Designs and SitePoint. He's a software engineer, and he understands that engineers deserve the leverage in this super competitive market where great engineers are at a premium. Check out hired.com/sedaily. I'm happy to advocate Hired to my listeners because it puts power in the hands of engineers. Now let's get on with this show. The History of Hadoop. An epic story about a passionate yet gentle man and his quest to make the entire internet searchable. The story begins on a sunny afternoon, sometime in 1997, when Doug Cutting, aka The Man, started writing the first version of Lucene. What is Lucene, you ask? Generally speaking, it is what makes Google return results with sub-second latency. Apache Lucene is a full-text search library. Okay, great. So what is a full-text search library? A full-text search library is used to analyze ordinary text with the purpose of building an index. An index is a data structure that maps each term to its location in text, so that when you search for a term, that index immediately knows all the places where the term occurs. Well, it's a bit more complicated than that, and the data structure is actually called inverted or inverse index, but I won't bother you with that stuff. The whole point of an index is to make searching fast. Like, imagine how usable Google would be if every time you searched for something, Google had to go through the internet and collect all the results. That's kind of ridiculous, right? You would want an index or some sort of data structure to do it for you. So it took Doug Cutting only 3 months to have something basically usable for his full text indexing project. A few years went by and Doug Cutting open sourced Lucene. He was surprised by the number of people that found the library useful and the amount of great feedback and feature requests that he got from those people. Just a year later, in 2001, Lucene moved to the Apache Software Foundation. By the end of the year, already having a thriving Apache Lucene community behind him, Doug Cutting turned his focus to indexing web pages. He was joined by University of Washington graduate student Mike Caffarella in an effort to index the entire web. That effort yielded a new Lucene subproject called Apache Nutch. Nutch is what is known as a web crawler or spider, a program that crawls the internet, going from page to page by following URLs between them. When Nutch fetches a page, Nutch uses Lucene to index the contents of the page and make it searchable. Working with Lucene and Nutch, Cutting and Caffarella made excellent progress. Nutch was deployed on a single machine with a single core processor, 1 GB of RAM, and RAID level 1 on 8 hard drives, amounting to 1 terabyte, then worth $3,000. With this one machine, Cutting and Caffarella managed to achieve a respectable indexing rate of around 100 pages per second. When applications are developed, a team usually just wants to get the proof of concept off of the ground, with performance and scalability as afterthoughts. So it's no surprise that the same thing happened to Cutting and Caffarella. The fact that they had programmed Nutch to be deployed on a single machine turned out to be a double-edged sword. Their prototype was simple and manageable, but it was limited by the total number of pages it could index on that single machine. They could only index 100 million pages. Understandably, no program could have indexed the entire internet on a single machine at that time. Well, even today, you wouldn't use a single machine. So, Cutting and Caffarella increased the number of machines to 4. Since they did not have any underlying cluster management platform, they had to do data interchange between nodes and allocate space manually because disks would fill up. This presented extreme operational challenge and required constant oversight. Any further increase in the number of machines would have resulted in exponential rise of complexity. Cutting and Caffarella desperately needed something that would lift the scalability problems off of their shoulders and let them deal with the core problem of indexing the web. The origins of Hdfs. Being persistent in their effort to build a web-scale search engine, Cutting and Caffarella set out to improve Nutch. What they needed as a foundation of the system was a distributed storage layer that satisfied the following requirements. It had to be schemaless, with no predefined structure, no rigid schema with tables and columns. It had to be durable storage. Once data was written, it should never be lost. It had to be capable of handling component failure without human intervention. This means that CPU and disk and memory and network and power supply could all fail individually on an individual component level without taking down the system as a whole. And finally, this distributed storage layer had to be automatically rebalanced to even out disk space consumption throughout the cluster. Cutting and Caffarella spent a couple months unsuccessfully trying to solve this tremendous set of problems. Fortunately, in October 2003, Google published the Google File System paper. When Cutting and Caffarella read the paper, they were astonished. It contained the blueprints for solving the very same problems they were struggling with. Cutting and Caffarella were already deep into the problem area, so they used the paper as the specification and started implementing their version of GFS in Java. It took them most of 2004, but they did a remarkable job. After it was finished, they named it the Nutch Distributed File System, or NDFS. The main purpose of this new system was to abstract the cluster's storage so that it would present itself as a single reliable file system. hiding all operational complexity from its users. In accordance with the GFS paper, the Google File System paper, NDFS was designed with relaxed consistency, which made it capable of accepting concurrent writes to the file system without locking everything down into transactions. This yielded substantial performance benefits. Another first-class feature of the new system was the fact that it was able to handle failures without operator intervention. This is important because failures happen all the time. The Google file system was created to be implementable on inexpensive commodity hardware components. How Google handled disk failure. When Google was still in its early days, they faced the problem of hard disk failure in their data centers. Since their core business revolves around data, they easily justified a decision to gradually replace their failing low-cost disks with more expensive, top-of-the-line ones. As the company rose exponentially, so did the overall number of disks, and soon Google counted hard drives in the millions. The decision yielded a longer disk life when you consider each drive by itself. But in a pool of hardware as large as Google's, it was still inevitable that disks would fail, almost by the hour. That meant that Google still had to deal with the exact same problem. So Google gradually reverted back to regular commodity hard drives and instead decided to solve the problem by considering component failure not as an exception but as a regular occurrence. Google had to tackle the problem on a higher level, designing the software system that was able to auto-repair itself. The Google File System paper states, "The system is built from many inexpensive commodity components that often fail. The system must constantly monitor itself and detect and tolerate and recover promptly from component failures on a routine basis." Following the GFS paper, Cutting and Caffarella solved the problems of durability and fault tolerance by splitting each file into 64 megabyte chunks and storing each chunk on 3 different nodes. In other words, they established a system property called Replication Factor and set the replication factor by default to 3. As I said, each chunk would be stored on 3 different nodes. In the event of component failure, the system would automatically notice the defect and re-replicate the chunks that resided on the failed node by using data from the other 2 healthy replicas. Mapreduce. Now that the operational side of things had been taken care of, Cutting and Caffarella started exploring various data processing models, trying to figure out which algorithm would best fit the distributed nature of NDFS. It was of the utmost importance that the new algorithm had the same scalability characteristics as NDFS. In other words, in order to leverage the power of NDFS, the algorithm had to be able to achieve the highest possible level of parallelism. It had to be near linearly scalable, such that 8 machines running an algorithm could be parallelized to be 2 times faster than 4 machines. So that is, the level of parallelism had to be good enough such that if you went from 4 machines to 8 machines, you get twice the speed. Cutting and Caffarella's idea was to somehow dispatch parts of a program to all nodes in a cluster, and then, after nodes did their work in parallel, collect all those units of work and merge them into a final result. In December 2004, Google published a paper by Jeff Dean and Sanjay Gamawat named Mapreduce, Simplified Data Processing on Large Clusters. Caffarella and Cutting thought it was brilliant. Mapreduce maps parts of a job to all nodes and then aggregates slices of work back to final result in the reduce process. The 3 main problems that the Mapreduce paper solved are: 1. Parallelization, how to parallelize the computation. 2. Distribution, how to distribute the data. 3. Fault tolerance, how to handle component failure. The core part of Mapreduce dealt with programmatic resolution of these 3 problems, which effectively hid away most of the complexities of dealing with large-scale distributed systems and allowed it to expose a minimal API, which consisted only of two functions, map and reduce. Inspiration for Mapreduce came from Lisp. So for any functional programming language enthusiast, it would not have been hard to start writing Mapreduce programs after a short introductory training. That's a testament to how elegant the API really was compared to previous distributed programming models. One of the key insights of Mapreduce was that one should not be forced to move data in order to process it. Instead, a program is sent to where the data resides. That was a key differentiator when compared to traditional data warehouse systems and relational databases. There's simply too much data to be moved around. To quote the Mapreduce paper, "We can generalize that map takes key value pair, applies some arbitrary transformation, and returns a list of so-called intermediate key value pairs. Mapreduce, then, behind the scenes, groups these pairs by key, and then becomes input for the reduce function. The reduce function combines those values in some useful way and produces result." Having heard how Mapreduce works, your first instinct could well be that it is overly complicated for a simple task of counting word frequency in some body of text, or perhaps calculating TF-IDF, the base data structure in search engines. And you would be right. There are simpler and more intuitive ways for solving those problems. But keep in mind that Mapreduce was designed to tackle terabytes and even petabytes of these sentences, from billions of websites, server logs, and click streams. Given that Mapreduce operates over large numbers of machines with giant amounts of data, we should talk about Mapreduce fault tolerance. Mapreduce jobs occur across numerous machines, and the job system needs to tolerate failures on the scale of the Google file system. Here is an excerpt from the Mapreduce paper, slightly paraphrased. The master pings every worker periodically. That is the master server, or the name node in more modern systems. So the master pings every worker periodically. If no response is received from a worker in a certain amount of time, the master marks the worker as failed. Any map tasks in progress or completed by the failed worker are reset back to their initial idle state, and therefore become eligible for scheduling on other workers. So to summarize, if a worker fails in the middle of a task, the master, or the name node, can tell another worker to fulfill that task. In July 2005, Doug Cutting reported that Mapreduce had been integrated into Nutch as its underlying compute engine. Engineers love automation, and Wealthfront automates your investing. As a software engineer, there are certain processes that you want to execute no matter what, like integration tests during a build. You wouldn't execute integration tests manually. You would use a continuous integration tool like CodeShip or Jenkins to automate your integration tests. Wealthfront is a tool to automate investing. Just like a continuous integration tool runs your tests automatically, Wealthfront can reinvest your dividends automatically and perform tax loss harvesting automatically. To get your first $15,000 managed by Wealthfront for free, go to wealthfront.com/sedaily and get started with Wealthfront's layer of automation on top of your portfolio. Wealthfront.com/sedaily. Check it out. It would support Software Engineering Daily, and you will get $15,000 managed for free if you sign up. Automate your investing. Get back to the things that you can't automate, like writing code. The Rise of Hadoop. In February 2006, Cutting pulled out Hdfs and Mapreduce from the Nutch codebase and created a new incubating project under the Lucene umbrella, which he named Hadoop. It consisted of Hadoop Common, the core libraries, Hdfs, the Hadoop distributed file system, and Mapreduce. At roughly the same time, in Yahoo, a group of engineers led by Eric Baldeschweiler had their fair share of problems. They were re-implementing Yahoo's search backend system for the third time. Although the system was doing its job, by that time, Yahoo's data scientists and researchers had already seen the benefits that GFS and Mapreduce brought to Google, and they wanted the same thing. But that's written in Java, engineers protested. How can it be better than our robust C++ system? As the pressure from their bosses and the data team grew, Yahoo made the decision to take this brand new open source system into consideration. Replace our production system with this prototype? You could have heard them saying. Baldeschweiler and his team chewed over the situation for a while, and when it became obvious that consensus was not going to be reached, Baldeschweiler put his foot down and announced to his team that they were going with Hadoop. In January 2006, Yahoo employed Doug Cutting to help the team make the transition. 6 months passed until everyone realized that moving to Hadoop was the right decision. In retrospect, we could argue that this decision was the one that actually saved Yahoo. Keep in mind that Google, having appeared a few years back with its blindingly fast and minimal search experience, was dominating the search market, while at the same time, Yahoo, with its overstuffed homepage, looked like a thing from the past. Yahoo's data science and research teams, now with Hadoop at their fingertips, were basically given freedom to play and explore the world's data. Having previously been confined to only subsets of that data, the world with Hadoop was refreshing. New ideas sprung to life, yielding improvements and fresh new products throughout Yahoo, invigorating the whole company. By 2007, other web-scale companies were starting to use this exciting new platform. Around this time, Twitter, Facebook, LinkedIn, and many others started doing serious work with Hadoop and contributing back tooling and frameworks to the Hadoop open source ecosystem. In February, Yahoo reported that their production Hadoop cluster was running on 1,000 nodes. 2008 was a huge year for Hadoop. At the beginning of the year, Hadoop was still a sub-project of Lucene at the Apache Software Foundation. In January, Hadoop graduated to the top level due to its dedicated and diverse community of committers and maintainers. Soon, many new auxiliary sub-projects started to appear, like HBase, a database on top of HDFS. Zookeeper, a distributed system coordinator, was added as Hadoop sub-project in May. In October, Yahoo contributed a higher-level programming language on top of Mapreduce called Pig. Facebook contributed Hive, the first incarnation of SQL on top of Mapreduce. This was also the year when the first professional system integrator dedicated to Hadoop was born, Cloudera. Cloudera was founded by a Berkeley DB guy, Mike Olson, Christophe Bishiglia from Google, Jeff Hammerbacher from Facebook, and Amr Awadallah from Yahoo. By March 2009, Amazon had already started providing Mapreduce hosting as a service, Elastic Mapreduce. In August 2009, Cutting left Yahoo and went to work for Cloudera as a chief architect, where he still resides. In 2010, there was already a huge demand for experienced Hadoop engineers. Yahoo's VP of Hadoop software engineering took notice of how aggressively the original Hadoop team was being solicited by other Hadoop players. Yahoo wasn't able to offer benefits to their star employees as these new startups could. These benefits like high salaries, equity, bonuses, etc. The road ahead did not look good. That was a serious problem for Yahoo, and after some consideration, Yahoo decided to support Baldishweiler in launching a new company. With financial backing from Yahoo, Hortonworks was bootstrapped in June 2011 by Baldishweiler and 7 of his colleagues, all from Yahoo, and all well-established Apache Hadoop PMC members dedicated to open source. For its unequivocal stance that all their work will always be 100% open source, Hortonworks received community-wide acclaim. Side note for context. In June 2012, Yahoo's Hadoop cluster counted 42,000 nodes. The number of Hadoop contributors reaches 1,200. Before Hadoop became widespread, even storing large amounts of structured data was problematic. The financial burden of large data silos made organizations discard non-essential information, keeping only the most valuable data, as if they actually knew what was valuable. Hadoop revolutionized data storage and made it possible to keep all the data, no matter how important it may be. And at this point in the blog post, Marco has an aside about the history of relational databases, and he has some interesting information taken away from talks by Clojure creator Rich Hickey. So I encourage you to read his blog post, which will be in the show notes for this episode if you want to know more about this aside. I'm going to go ahead and skip ahead to the next part of the Hadoop history. Enter Yarn. Where Hadoop was lacking the most was knitting. Although huge clusters of looms, powered by Mapreduce, were happily weaving away, it became increasingly obvious that more serious wool-working machinery was due for a change. Enter Yarn. You may have heard of Yarn, but don't know what it does. Yarn stands for Yet Another Resource Negotiator, and we're going to talk about how we got there. Now seriously, where Hadoop version 1 was really lacking the most was its rather monolithic component Mapreduce. The root of all problems was the fact that Mapreduce had too many responsibilities. It was practically in charge of all functionality above the Hdfs layer, assigning cluster resources and managing job execution, doing data processing and interfacing towards clients. Consequently, there was no other choice for higher-level frameworks other than to build on top of Mapreduce. The fact that Mapreduce was batch-oriented at its core hindered the latency of application frameworks built on top of it. The performance of iterative queries, usually required by machine learning and graph processing algorithms, took the biggest toll. Although Mapreduce fulfilled its mission of crunching previously insurmountable volumes of data, it became obvious that a more general and more flexible platform atop Hdfs was necessary. In August 2012, the final decision was made. The next generation data processing framework, Mapreduce v2, codenamed Yarn, Yet Another Resource Negotiator, was to be pulled out from Mapreduce codebase and established as a separate Hadoop subproject. It had been a long road until that point, as work on Yarn was initiated back in 2006 by Arun Murthy, one of the Hortonworks founders. As a side note, I'd love to get Arun on the show, so if he's out there, please contact us, or we'll contact you. In order to generalize processing capability, the resource management, workflow management, and fault tolerance components were removed from Mapreduce, a user-facing framework, and transferred into Yarn, effectively decoupling cluster operations from the data pipeline. And just to deliver the gravity of how crucial Yarn was, you should check out a diagram of this that we'll put in the show notes where you see how Yarn is pulled out as this interfacing layer that gives rise to all these other frameworks that I'm about to talk about. The emergence of Yarn marked a turning point for Hadoop. It has democratized the application framework domain, spurring innovation throughout the ecosystem and yielding numerous new purpose-built frameworks. Think Storm, Spark, plenty of other things. Mapreduce was altered. in a fully backwards compatible way so that it now runs on top of Yarn as one of the many different application frameworks. The hot topic in Hadoop circles is currently main memory. There are plans to do something similar with main memory as what Hdfs did to hard drives. Different classes of memory, slower and faster hard disks, solid-state drives, and main memory RAM should all be governed by Yarn. Application frameworks should be able to utilize different types of memory for different purposes as they see fit. This brings us to Spark. Apache Spark brought a revolution to the big data space. By including streaming, machine learning, and graph processing capabilities, Spark made many of the specialized data processing platforms obsolete. Having a unified framework and programming model in a single platform significantly lowered the initial infrastructure investment, making Spark that much more accessible. Up until now, similar big data use cases required several products and often multiple programming languages, thus involving separate developer teams, administrators, code bases, testing frameworks, etc. This concludes the story of Hadoop until the present. We hope you have enjoyed this episode of Software Engineering Daily. Thanks again to Marco Bonaci for letting us turn his fantastic Medium post into a full episode. Listeners who are interested in the future of Hadoop, if you're compelled by Marco's take on the story, you might believe that Spark is the place to look. And Marco's book, Spark in Action, is probably a great place to start. I guess I can't vouch for the book itself because I haven't read it, but granted how compelling his story of Hadoop was and how clear and well-researched it was, I have no doubt, well, I have very little doubt that his Spark book is excellent. I can't vouch for it again because I haven't read it, but you should check it out. So Marco Bonaci, follow him on Twitter, follow him on Medium. We'll see you next time on Software Engineering Daily.